Every single time your heart beats, it's writing a story. It's this tiny, invisible electrical drama that plays out billions of times a day inside you. We see the result, that familiar waveform on an ECG screen. But what is actually happening on a microscopic level? Well, today we're going to dive in and uncover the electrical story of one single heart.
So, what is that story? To really understand it, we have to zoom in. I mean, way, way in, past the organ itself, past the muscle tissue, all the way down to a single heart cell. And we're going to watch it generate the very electricity that powers your life. Okay, so before a heart cell can actually fire, it has to be ready. You can think of it like a tiny biological battery, just sitting there, fully charged, waiting for a signal. This resting state, it's the foundation for literally everything that's about to happen. Now, this charged state, it has a name. It's called polarization. The cell's outer skin, its membrane, works incredibly hard to separate positive and negative ions. And by doing that, it creates this state of electrical potential. It's just primed for action, exactly like a battery. So how does it do that? How does it hold that charge? Well, the secret is all in the chemistry. Outside the cell, you've got a sea of positive sodium ions. But inside, there's a different mix. You've got some positive potassium ions, sure, but they're swimming around with these big, heavy, negatively charged proteins. And that imbalance, that's the whole secret. It's what makes the inside of the cell electrically negative compared to the outside. And get this isn't just some abstract idea. It's a real, measurable voltage. If you could stick a microscopic probe inside a resting heart cell, you would measure a charge of about -90 millivolts. That's its resting potential. That's its stored energy right there. Okay, so the battery's charged, the cell is resting. Now what? What happens when it finally gets the signal to beat? This is where the magic happens. All that stored energy gets released in a sudden, really dramatic wave.
It all kicks off with a trigger, an electrical nudge from a neighboring cell. And this trigger completely changes the cell membrane. All of a sudden, it becomes incredibly porous to all of that sodium that's been waiting outside. And bam, the floodgates just swing wide open.
What happens next is this perfect, lightning-fast chain reaction. First, the trigger arrives. That opens the gates, which lets all those positive sodium ions rush in. This completely flips the cell's internal charge from negative all the way to positive. And that flip instantly triggers the next little bit of the cell, and the next, creating this incredible electrical wave that just shoots down its entire length, kind of like falling dominoes. And this moving wave of positive charge, it's got a name. We call it depolarization. This is the action part of the action potential. It's the electrical event that is ultimately going to cause the muscle to contract. Okay, so this is all happening at a microscopic level, right? An invisible wave of electricity moving through a single cell. So how on earth does a big machine with electrodes stuck to your skin actually see it? Let's connect the dots from the cell to the screen. And here's the absolute key to understanding this whole thing. Any moving wave of electrical charge, like our depolarization wave, generates a small electrical field around it. It's this field that radiates out from the heart through your body all the way to the skin where those ECG electrodes can pick it up.
Now, let's talk about the first fundamental rule of reading an ECG. It's actually super simple. When that wave of positive charge, that depolarization wave, is traveling towards a detecting electrode, the machine draws an upward line. That's it. Towards means up.
And the size of that upward spike? It all depends on how close the wave is. As the wave gets closer and closer to the electrode, the electrical field it detects gets stronger, and the line on the screen goes higher and higher, creating a peak. Right when the wave is directly under the electrode, that signal is at its absolute maximum.
But, what goes up must come down, right? A cell can't just stay depolarized or fired forever. It has to reset itself to get ready for the very next beat. And this reset process, it's every bit as important as that initial spark. This reset is another electrical wave, but it's a different beast altogether. It's called repolarization. Its whole job is to restore that original -90 millivolt charge. It's It's essentially recharging the battery.
So what's happening now is that channels for potassium open up, and all those positive potassium ions start flowing out of the cell, which of course makes the inside negative again. Now, what's really fascinating here is that this reset wave, it often travels in the opposite direction of the initial firing wave, and it happens much, much more slowly.
All right, so we've got our two main players, the fast firing wave of depolarization and the slow resetting wave of repolarization. So now let's imagine we place an electrode nearby and just watch as it draws that iconic shape of a single heartbeat. Here's how the ECG tells the story. As that fast-firing wave comes towards the electrode, the pen shoots up, creating that sharp, tall R wave. As the wave passes by and starts moving away, the pen dives down, drawing the S wave. Then, things pause for a second. And finally, as that slow reset wave approaches, the pen draws a much slower, gentler, wider bump. And that's our T wave. So you can think of it just like this. A fast approach gives us the sharp R wave. A fast departure gives us the sharp S wave. And that slow, final reset process gives us the wide T wave. Each part of the shape is telling a specific part of our electrical story. The shape of that wave tells you everything about the speed of what's happening. The R wave is so tall and sharp because that flood of sodium ions, it's an incredibly rapid and electrically powerful event. It's like a tiny explosion of positive charge. And then you've got the T wave, which is a totally different story. It's lower and it's much wider. Why? Well, it's because repolarization, that slow outflow of potassium ions, is just a more gradual, drawn-out process. The machine is simply recording a weaker electrical event that's happening over a longer period of time. And check this out. Here's a stunning fact about the timing. The actual firing part, the R and S waves, that's lightning quick. But the reset process, the T wave, that takes more than twice as long. Think about that. It means your heart cells spend most of their time carefully, methodically preparing for the next beat. So let's just bring it all home. When you really think about it, that simple line on the screen, it's not so simple at all, is it? Every single peak, every valley is a direct echo, a visible signature of this microscopic electrical ballet of ions flowing in and out of a single cell. It's just incredible to think that one single cell can tell such a complex, such a vital story over and over again without ever missing a beat. It really makes you wonder, doesn't it? What story is your heart telling right now?